Okay, well, this genuinely sucks. I had three problems recorded. It was like an hour video that could have been cut down to maybe 30 minutes, and that was my third attempt at making those problems. So really, it took more. But and then I was recording on my iPhone, projecting to my computer, but I guess my iPhone tweaked or something because the footage was corrupted, and now I'm kind of pissed. So I'm gonna be recording this on my photo booth. Hopefully, you can see this then. Um, and I'm gonna try to do maybe two, just one. They're all thermochemistry related, so like chemistry stuff. I'm gonna try to go through it quick. Already wasted a minute. Yeah. So these are two chemistry problems because these seem to be the ones people are most worried about. So I just do that. This is for the combustion final. Yeah. This is it's 4:20 in the morning, and I wake up at 10. So cool stuff. Cool stuff. Okay. So which one should I start first? I'll do this one. This one evens out pretty well. I don't even know the name. Isocetine? I think I wrote it wrong. It's C8H18 is burned with air in an engine at an equivalence ratio of 0.8333. Assuming complete combustion, write the balance equation and then find the air-fuel ratio of the real case and how much excess air in a percentage. So, I'll start off with chemistry basics. If I have, let's say, 8H2O, then if I was counting how many hydrogens I have 8 times 2, which is 16 hydrogens. And then the number in the front always acts as a distributor essentially. So that means I also have 8 oxygens, and there's no number here, so it's just 8. 8 oxygens. But for solving these or balancing these equations, I'm typically going to have like a variable here. So let's say, I don't know, x. That means in this case I have 2x hydrogens and I have x amount of oxygens. That's just like the basics. Another rule of thumb for this kind of thing, hydrogen molecular weight is 1 gram per mole. 1. Carbon is 12. Oxygen is 16. And nitrogen is 14. That's just kind of something you should know. Helium is 2. Maybe lithium is 3 or 4. I don't remember. But these are the ones you should know and remember. And then one last thing, the molecular weight of air is roughly 29 grams per mole, because we're going to be using that a little bit. So with that, we can begin. So the fuel we're using is C8H18. And typically when you're doing these problems, when you're solving for either the real case or the stoichiometric case, in this case we're going to solve for the stoichiometric, it's going to follow this sort of format where it's fuel plus O2 plus 3.76 N2. This is the reactant side. plus CO2 plus H2O plus N2. This is the stoichiometric case. For the real case, depending if it's fuel rich, you might have this fuel on this side as well. If it's air rich, you might have oxygen on this side, so O2. But in this problem, we don't need to know the real case, we just need a stoichiometric case. The reason we don't need the real case is because we have the equivalence ratio. So this is the general format. You should memorize that this is always going to be on the product, and this is always going to be in the reactant side. So let's do this. C8H18. Okay. So our fuel is C8H18 plus our O2 plus 3.76 N2. It's always going to be that number. And then our products, it's going to be CO2 plus H2O plus N2. Again, this is for stoichiometric. It's pretty much always going to look like this, depending on your fuel. This is going to change, but everything else is the same. Also, stoichiometric, you're assuming all your fuel is burned, it's completely gone, and also it's perfect, so we're just going to put 1 here, and then we'll put an alpha here, we'll put a beta here, gamma, and an omega. Yeah. Now, let's just work down the line. So, how many carbons on the left versus how many right, and then we'll do it for each element. So, we'll start off with carbon. How many carbons on the left? We have 1 times 8. That's it on the left, so we have 8 carbon on the left. Right here we have beta times carbon, and that's it. So we get beta times 1, which is beta. So we have beta equals 8. So I can replace this with an 8. We'll start off with, we can go with hydrogen next, but let's do oxygen. Just in case you get stuck, doesn't mean you could stop, you could find another element, right? So right here, I'm going to get alpha times 2, so we'll call it 2 alpha. And then on the right side, we have 8 times 2, which is 16, plus gamma times 1, which is gamma. This is alpha, not gamma. And right here we have 2 unknowns, so I can't solve here, so I should just go to the next one. So let's go to hydrogen next. So we have 1 times 18, which is 18. And then nothing else on the left. Right side we have gamma times 2, which is 2 gamma. And then we only have 1 unknown, so gamma equals 9. If gamma equals 9, I can plug that to here. So it's 16 plus 9, all divided by 2, which is 12.5, right? Yeah. So I'll just put 12.5 here. And then for nitrogen, this one's important. It's 12.5 times 3.76. And then don't forget there's a 2 here, so it's also times 2, which equals omega 2, which is 2 omega. Solve for omega and you get 12.5 times 3.76, which I think is 47, but I'm just going to write, I'll write 47, who cares? I think it's 47, right? Yeah. So this is the stoichiometric formula for that. Now from there we could find the air-fuel ratio for the real case without even having to solve for its equation. So, what is air-fuel ratio? Air-fuel ratio is going to be the number of moles times the molecular weight of air over the number of moles times the molecular weight of fuel. This is used for the real case and the stoichiometric case. The equivalence ratio is the air-fuel ratio of the stoichiometric case over the air-fuel ratio of the real case. Now the reason I say we don't need to solve for the real case is because we could get for the stoichiometric case of the air-fuel ratio, and we have the equivalence ratio, so we could just solve for this directly. So let's do that. And I'll just put an S here because this is the stoichiometric case. All right. The number of moles of the air is going to be 12.5 times 1 plus 3.76, because you're always taking the coefficients of whatever you're doing for this one, for the number of moles, right? So you have a 12.5 here, so 12.5, and then the coefficient before O2, which is 1, and the coefficient before N2, which is 3.76, so it's going to be 1 plus 3.76, right? So that's your number of moles for air. And now you need to multiply it by the molecular weight of air, which I said before was roughly 29 times 29. The number of moles of the fuel is this coefficient, which is just 1 times the molecular weight of the fuel, which I said earlier, one carbon is 12 grams per mole. One hydrogen is 1 gram per mole. So it's going to be 1 times 8. Or no, it's going to be 12 times 8, which is, I don't know, 12 times 8 plus 18 times 1, which I think this is like 114 at the bottom. Yeah. So if you solve that, you get about 15.2, I think. Right? Yeah. Okay. And since we know the stoichiometric case, yeah, this AFS over AF real, this is 0.8333 equals 15.2. AF real is going to be 18.2 roughly. So that's how you solve that. And for the excess air, pretty easy. Call it EA Sports, percentage, excess air. It's going to be 1 over the equivalence ratio minus 1 times 100, which in this case, it gives us roughly 20%. Now, if it's positive 20%, that means you have more air than fuel. And let's say if it's solved to be negative 20%, then you will have more fuel than air. So there you go. So if the problem says it's fuel rich, this should probably be a negative number. If it, let me take that away. If the problem says it's lean fuel or lean burn, it's probably more air than fuel. So it should be a positive excess air. So, with that, I'm going to do the second one as quickly as I can. I won't explain the problem. I'll just write down the fuel. I'll explain it in short. So we have C4H8 is burn, fuel rich. That should tell you something. The exhaust is 14.95% CO2. It has fuel on the side, which is 0.75%. And then nitrogen is the rest of the percentage. So our fuel is C4H8. So I'll write that C4H8 again O2 plus 3.76 N2. This one's long, so I should just write it here. And then we know it's 14.95 CO2. We don't have that for H2O, so I'll just write that plus 0.75 C4H8 plus 8, it was 84, 84.3 N2. Call this one alpha, beta, omega. So this is given in the problem. We have C4H8, and they also say we have 14.95% gas as our exhaust. We have 0.75% as C4H8, and the rest is N2, which is 84.3 if you add these together and minus 100, or 100 minus those two added. They didn't say anything about water, but it is there because it's the basic combustion formula. It should be there. Yeah. And then in this case, this is the real case, and we could solve for the stoichiometric case. I think we have to later, but the reason we're solving for the real case is because they so graciously gave us the percentages of most of it, so you could just solve for the real case pretty simply. So, and since this isn't stoichiometric, we're going to have a variable in front of the fuel. So, I mean, most of it's just solved. We just need alpha, beta, and omega. So we could just go one by one, which I'm going to have my notebook with me. So for carbon on the left, it's going to be alpha times 4. So I'll write carbon, and then, interesting, I did nitrogen next, okay. And then hydrogen. So for carbon, we have 4 alpha here, so 4 alpha equals 14.95 carbon here, plus 0.75 times 4. So that means alpha is going to be equal to 4.5. And then I can replace this here. 4.5. And then we can start off, or our next one's going to be, I guess it would be nitrogen, huh? We could do nitrogen next. You could do oxygen next. You could do hydrogen next, but I chose nitrogen here. So nitrogen on the left is going to be beta times 3.76 times 2. So I'll write that 2 times 3.76 times beta, which on the right side, the nitrogen equals 84.3 times 2. So 84.3 times 2. Beta equals, I'll get rid of that, 22.4. And then hydrogen on this side is going to be tweaking. So it's going to be 4.5 times 8 times 2 omega plus 8 times 0.75. And then if you solve for omega, you get 14.95. Which, plug those back in, and that's your Steph. Did it connect back? No. Yeah. Okay. Which, I'm not going to plug it back in, but bam, bam, there you go. So this is your balanced chemical equation for the real case. And then from there you could get the air-fuel ratio, which is air-fuel for real is going to be equal to number of moles times molecular weight, air, over number of moles times molecular weight, fuel. So in this case, the number of moles for the air is going to be beta, which is 22.4, times 1 plus 3.76. So it's going to be equal to 22.4 times 1 plus 3.76. And then the molecular weight of air is 29, so I'll put 29 here. The number of moles for the fuel is going to be 4.5 times the molecular weight of this fuel, or the number of moles is 4.5. Molecular weight of fuel is going to be 12 times 4 plus 8 times 1, which is a number, I guess. $12.32. So that's for your real case. And then we could solve for the stoichiometric case. And let me repeat this. The stoichiometric case, always assume that the fuels burn just right, so you're not going to have this fuel case on the product side. And then you always assume fuel is just going to be 1 as your number of moles, so get rid of that number. And then that breaks everything else, so you're just going to have to recalculate everything. So I'm going to get rid of all the numbers in the front. Get rid of nitrogen for a second. So this is N2 here. And then let's redo this. So we have 1 in the front here. We have alpha, we have beta, we'll call this one omega, and then it's another Greek letter, epsilon. There you go. That looks a lot less like alpha. So I could just do this real quick. Well, no. Okay. We'll start with carbon. We'll just make our way down. Carbon, we have 4 here, and we have beta here. That means beta equals 4. Get rid of that. Q. For hydrogen, we have 8 here, and we have 2 omega here. So 8 equals 2 omega. That means omega equals 4. Get rid of this. For oxygen, we have 2 alpha, and then here we have 8 plus 4. That means alpha equals 6. And then for nitrogen, we have alpha times 3.76 times 2 equals 2 epsilon. We know alpha is 6, So to solve for epsilon, you get 6 times 3.76, which I guess is, it's a number, I don't know, whatever that equals. And from there, you can solve, let me plug that in. Alpha is 6 here. This is 6 times 3.76. There it is. So this is the stoichiometric case of the combustion of this fuel. So they get the air-fuel ratio. Again, let me repeat this. Air-fuel ratio is number of moles times molecular weight of air over the number of moles times molecular weight of fuel. So the number of moles for the air is going to be 6 times 1 plus 3.76. So it's going to be equal to 6 times 1 plus 3.76 times 29, because that's the molecular weight of air, over the number of moles of fuel, which in this case is 1, times 56. 56 is 12 times 4 plus 8, that. Which, if you do that, you get 12, nope, hold on, 14.79. And this is for your stoichiometric case. So, we're almost done here. Where's my napkin? What? Where'd it go? What? Okay. What? Where? There it is. Okay. Alright, so to get the air, or the equivalence ratio, let me repeat this, is going to be air-fuel stoic over air-fuel real, which we said was like 14.8 roughly, and this is 12 point, where is it, I lost it, 12.3. So this this equivalence ratio is going to be roughly 1.2. And so to get the excess air now, it's going to be 1 over the equivalence ratio minus 1 times 100, which yields negative 16%. Now, if you recall, a negative number means that we have more fuel than air, which makes sense because at the start of the problem we said this system is fuel rich, so yada yada, bada bing, bada boom. Or I guess not more fuel than air, then more so more fuel than the combination. You can't combust all the fuel with the amount of air you had. Let me say that. With that, I'm going to sleep. I'm still kind of bummed out the other video got deleted, but whatever.